In this video, we'll be covering the entirety of the electrolysis topic in this specification. So we'll start off with some basics, looking at 1.55 and 1.56C, understanding why covalent compounds do not conduct electricity, and why ionic compounds do, but only in molten or in aqueous solutions. Look at some terminology in 1.57C, looking at anions and cations and how they are used to refer to negative and positive ions respectively. We look at some experiments in electrolysis and the list of compounds that you need to know how to represent the electrolysis of. And then we move on to writing ionic half equations to represent these reactions. And finally, looking at 1.60, a practical that you might do in the lab to have a go at this yourself. It feels as though we've covered this before in previous videos on covalent bonding. However, since it comes up again, I'll go through it again now. Now, typical covalent compounds don't conduct electricity. Okay? This is because, if you remember, they form simple molecular structures that have weak intermolecular forces between the molecules. There are no ions that are free to move, and there are no delocalized or free electrons that can move. And therefore, they don't conduct electricity. So in the diagram on the left, we've got representation of, say, a diatomic gaseous compound like oxygen or hydrogen. And we'll have these weak intermolecular forces between the molecules. Notice that nowhere on this diagram are there any free electrons or ions. Therefore, we have no free electrons, no free ions, no conduction of electricity. Likewise, we covered this when we did ionic bonding, but again I'll go over it here. So, ionic compounds don't conduct electricity when they're solid. This is because they form a fixed lattice, okay? And therefore the ions in the lattice are not free to move. If they can't move, we can't conduct electricity. There are also no delocalized electrons. So we can use our electrical conductivity checklist and see that it, of course, does not conduct electricity. However, when you melt them, the lattice breaks down, the ions are no longer in a fixed position, and they can then move, which means ionic compounds in aqueous solution or when molten do conduct electricity. And if we use our checklist, we can see that there's no free electrons, but there are free ions, so it does conduct electricity. But what actually is electrolysis? Well, electrolysis means breaking with electricity. And in a sense, what it really is a separation technique. What we're doing is separating the ions within ionic compounds. Now what we do is we pass an electrical current through a molten or an aqueous substance. And what this does is causes the ions within it to move to the oppositely charged electrodes. Now, just a note, we use inert electrodes, which are unreactive, normally made of graphite. This is just to make sure that they don't participate in the reaction. Now, within our electrolysis, we'll have two different types of ion. We have an anion, which is negatively charged, which I mark as A- for now, and we have a cation, which are the positively charged ions, which I'll use as C+. Now, of course, they move to the oppositely charged electrodes, so the cation, being positively charged, will move to the cathode, which is negatively charged, and anion, being negatively charged, will move to the anode, which is positively charged. The way to remember this is the name of the electrode tells you which kind of ion is attracted to it. So now for an example. On the left here, we have the electrolysis set up for the electrolysis of molten sodium chloride. So we've taken sodium chloride, we've melted it, and now we have sodium chloride in a liquid form. So we have Na1 plus ions and chloride 1 minus ions moving freely around the liquid. Once we turn on our electricity, the ions will be attracted to the electrode that has the opposite charge to themselves. So you can see that the Cl1 minus ions have moved over to the positively charged electrode, and the Na1 plus ions have moved to the negatively charged electrodes, i.e. the Cl1 minus anions have moved to the anode, and the Na1 plus cations have moved to the cathode. Now what happens at each of these electrodes is slightly different. So at the anode, the chloride 1 minus ions will lose one of their electrons, and they'll form chlorine atoms. Two of these chlorine atoms then bond together, forming chlorine gas, which you'll see bubbling off. This could therefore be tested for using damp litmus paper. At the cathode, sodium ions will actually gain an electron, and form sodium atoms. This will therefore form sodium metal at the cathode. Point 1.58 in the specification provides that you have to know how to do this for lead-2-bromide specifically, and be able to apply these concepts to any molten ionic compound. So we'll go through lead bromide first, but you'll see, just like with sodium chloride in the previous example, that the concepts are exactly the same each time. On the left hand side, we've got Pb2+, that's lead 2+ ions, moving around in the liquid with Br1-, that's the bromide ion. Once we turn on the electricity, the bromide ions will go to the anode because they're anions, and the lead 2+ ions, being cations, will go to the cathode, which is negatively charged. At the anode, the bromide ions will lose an electron and form a bromine atom. Two of those then bond together, forming bromine, which is a brown liquid at room temperature. At the cathode, in this case, those lead ions will gain 2 electrons to form lead atoms, and therefore lead metal will be seen forming at the cathode. Before we move on, it's time for you to have a try. Here is the electrolysis of iron 2 iodide. This consists of Fe2+ ions and iodide 1- ions. I've put a blank version of the diagram here for you to consider, and what I'd like you to try to do is figure out what happens at the anode, what happens at the cathode, and what are the products that are produced at both of those places. Pause the video and have a try. Okay, so in our system we have iron 2+ ions, Fe2+, and iodide 1-. I won't write in all of those, it'll take too much time. All of the orange ones are iodide 1-, and all of the green ones are iron 2+. Now, once we turn on the electricity, they'll of course be attracted to the opposite charged electrodes. That means that our iron 2+ ions will go to the cathode, and our iodide 1- ions will go to the anode. So, at the anode, those iodide 1- ions will lose an electron and form iodine atoms. Two of those will then bond together, forming iodine. Now, at the cathode, those iron ions will gain 2 electrons and form iron atoms. Iron metal will then be seen collecting around the cathode. Electrolysis of aqueous solutions. Here's where things get a little bit more interesting. Now, an aqueous solution is formed when an ionic compound is dissolved in water. What this means is you end up with 4 different ions present. The H+ ion, the OH- ion from the water, and then the 2 ions from the ionic compound. In this case, we'll use the example of sodium chloride, in which case you get the Na+ ion and the Cl- ion. Now, only one of each type of ion, so only one negative and one positive, can interact with each of the electrodes. That means we have to figure out which one goes where. And to do that, we use discharge preference rules. So, at the anode, if the anion is a simple ion, like chloride or bromide or iodide, it will be preferred, so it will go to the electrode. If it's a complex ion, it will stay in solution, and the OH- ion will go to the electrode. In this case, we have a simple ion, so the chloride ion will go to the anode. Now at the cathode. Now here's where we're concerned with the reactivity of the metal when compared to hydrogen. So you'll need your reactivity series for this. Now, if the metal is more reactive than hydrogen, then the H+ ion will be preferred, and it will go to the cathode. If the metal is less reactive than the hydrogen, then the metal will go to the cathode, leaving the H+ in solution. Now in this case, sodium is more reactive than hydrogen, and therefore the H+ ion will go to the cathode. So following on from that example, let's do this one properly then. We have our 4 ions in solution. Let's do our anode first. So the chloride ion, being a simple ion, will be preferred over the hydroxide ion. So it will go to the anode, it will lose its electron, it will bond to another chlorine atom, and it will form chlorine gas, which bubbles off. Okay, so you'll see bubbling. And at the cathode, we have to, of course, compare the reactivity of sodium with the reactivity of hydrogen. And as I previously mentioned, sodium is more reactive, which means that the hydrogen comes off at the cathode, and it will gain electrons there. It will bond to another atom, and it will bubble off as H2 gas. So you'll see bubbles here of hydrogen and bubbles on this side of chlorine. Now what you leave behind in the solution is going to be NaOH. This is how we make sodium hydroxide in industry. Now there are a few other aqueous solutions that we need to know how to do the electrolysis for. And this is the second one, dilute H2so4. Now what we're actually doing here is electrolyzing water, but you can't electrolyze water without an electrolyte. So we add a little bit of H2so4. So again, what do we have here? We have 4 ions in solution. Now the water dissociates into H plus and OH minus, and the H2so4 dissociates into H plus and SO4 2 minus, which means we actually now only have 3 ions in solution because both the water and the sulfuric acid produce H plus cations. So obviously we're going to get H plus ions going to the cathode and producing hydrogen gas. Okay, now looking at the anode, we have to decide whether the sulfate ion comes out or whether the OH minus ion comes out. Now if you recall, if it's a complex ion, then the anode will prefer the hydroxide, so the hydroxide goes to the anode and it will form oxygen gas and water. So you'll see bubbles of oxygen gas coming off. Okay, so the last aqueous solution you have to know how to do the electrolysis for is for aqueous copper sulfate. Now the only difference between aqueous copper sulfate and dilute H2so4 is in that you have the copper 2 plus cation instead of the extra H plus. So of course we have the same situation at the anode. The OH minus ion is preferred by the anode and that produces oxygen gas and water, which of course would stay in solution. And in this case, because copper is less reactive than hydrogen, the copper will go to the cathode. And what you'll actually see is copper metal forming a layer around the outside of the cathode. The final thing you have to be able to do with regard to electrolysis is to write half equations that represent the production of the products at each of the electrodes. Now in electrolysis, half equations just show what's happening at each electrode. They show either the addition of electrons, i.e. reduction, or the loss of electrons, i.e. oxidation. Now this process of reduction or oxidation leads to the conversion of ions into atoms or molecules. So for example, like in the last example we just did with the electrolysis of copper sulfate solution, we have copper 2 plus ions going to the cathode to gain electrons. We represent electrons with E minus. Now of course we'll need 2 electrons per copper atom because it's a 2 plus ion, and that will form copper metal. Alternatively, at the anode we could have something like the chloride ion losing electrons to form chlorine gas. Now you'll see that this is unbalanced at the moment. We need 2 chloride ions to form 1 chlorine molecule, and of course 1 electron is lost per chloride ion, which means we need to have 2 E minus there. Now one thing to note is that we never subtract electrons in half equations. So you might be tempted to think that I could have written 2Cl minus minus 2E minus goes to Cl2. That looks okay. However, by convention, we never minus electrons, we only add them. So what we do instead is if something loses electrons, you add them to the other side. This might seem confusing for now, but I'm sure it will make sense as we move through the following slides. So what's good about this is that although people struggle with half equations, there actually aren't many that you have to be able to do. So there isn't an infinite list of things, there's only a short list, and once you get the gist of them, you can actually memorize them as opposed to learning how they work. I would recommend, of course, learning how they work. They are actually quite simple and it sets you up well for A-level and for further understanding generally. So looking at point 1.58C, we need to know to be able to write half equations for the following experiments. So for any molten ionic compound, okay, so not just lead bromide, and then for aqueous sodium chloride, dilute sulfuric acid, and aqueous copper sulfate. So we'll do those one by one, and you'll see that it's really quite easy. So we'll start with the simplest one, the electrolysis of molten lead bromide. So because it's molten, we only have the lead 2 plus ions, the Pb2 plus, and the bromide ion, Br1 minus. Now at the anode, the bromide ion will lose electrons, So of course we're adding electrons to the side, okay? And it will form bromine, which is Br2. So all we have to do then is to balance it, and we need to make sure we have 2 bromide ions and 2 electrons. At the cathode, the lead ion, the Pb2+, will gain 2 electrons to form lead metal. Simple. Okay, so for another example of molten electrolysis here, I've picked silver iodide, because in an exam you could be given any combination of metal with non-metal here, just to demonstrate exactly the same process that we've just carried out with the lead bromide. So it's exactly the same. So I recommend at this stage, perhaps pause the video, see if you can write the half equations, and then check you're working against mine. Okay, so same situation here. The iodide ions, I-, will lose electrons, so we add them to the other side. They will form I2 because it's diatomic, and we therefore need to balance it, so it's 2I- goes to I2 plus 2 electrons. For the cathode, the silver ion will gain 1 electron because it's only 1 plus, and it will form silver metal. So now for the more complicated ones. There's only one extra step though, and that's deciding which one will go to each electrode. So looking at the anions, we know that chloride ions are simple ions, so they will be preferred over the hydroxide ions. And of course, sodium is more reactive than hydrogen, therefore the hydrogen will go to the cathode. Therefore, at the anode, we have our chloride 1- ions. We'll have 2 of them. Each one will lose an electron, and it will form Cl2 gas. And at the cathode, hydrogen ions will gain electrons and form H2. Now, of course, because we've got H2, we need 2 H+ ions and 2 E- electrons. Half equations for the electrolysis of dilute H2so4 can be figured out as follows. So again, we look at our preference rules. Now in this case, we've got the sulfate ion, which of course is never preferred. Okay, so in this case, the OH- ion will go to the anode, and we have the equation. This is the most complicated one that you have to do. So you get OH-, and that will form water and oxygen. Okay, and of course it has to lose some electrons. Now we need to balance this. The way to balance this is to have 4 OH-, 2 water molecules, and 1 oxygen molecule, and then of course you lose 4 electrons. Now on the other side, of course, we've only got hydrogen ions here, so we have the same as before, so it's going to be 2H+ plus 2E- goes to hydrogen gas. And finally, half equations for the electrolysis of aqueous copper sulfate. So again, we go to our rules, and we know that when we have a hydroxide ion and a sulfate ion in there, because the sulfate ion is a complex ion, the hydroxide is favoured, and we get 4 OH- going to 2 H2O plus O2 plus 4 electrons. At the cathode, we get the metal coming off because it's less reactive than hydrogen, and in this case, of course, we have copper 2+ ions that will gain electrons. It will have to be 2, of course, to form copper metal. So finally, for this topic, you'll likely do a classroom practical where you set up electrolysis using a beaker, a power pack, some graphite electrodes, because of course, as I mentioned, they're inert, and you'll electrolyze normally an aqueous solution. There's a demo that often gets done for lead bromide, and you might get to see that from one of the teachers showing that if you're lucky. However, if you're going to do it as a class practical, you'll likely be electrolyzing perhaps sodium chloride solution. Now, what you'll be doing most likely is collecting the gases that come off at each of the electrodes and then testing them by combining them with your knowledge from other parts of the course to prove what those products are in fact. So you'll collect a gas coming off of the anode, and if it bleaches damp litmus paper, then of course that would be chlorine gas. Or of course you might collect a gas that gives a squeaky pop when ignited, in which case you've proven that you've got hydrogen gas coming off. And likewise, if you've got oxygen gas, then of course it would relight a glowing splint. This is something that you'll have to do in class, and you'll get much more understanding with when you've actually done it physically. So how is this content examined? Well, typically it's examined in conjunction with the bonding topic, because of course our understanding of the electrical conductivity of ionic and covalent substances is related to their bonding. So we already know why ionic compounds conduct electricity when molten or in solution, and why covalent substances don't conduct electricity. But you might then be asked to predict the products of the electrolysis of something, or you might be asking indeed to prove that the products of electrolysis of something are or aren't what the question suggests. So you have to use your knowledge of chemical testing to test for hydrogen, for oxygen, or for chlorine, or something else. And then finally, the higher level questions, you might be asked to write half equations for the formation of the products of the electrolysis of something, and therefore explaining whether each is considered oxidation or reduction. So if something's gaining electrons, then of course it's reduction, and if something is losing electrons, then of course it's considered oxidation. Thank you for watching Cardinal Science. If you found this useful, please leave a like and subscribe. It's really helpful if you do, and leave a comment if you have any suggestions or requests for further videos. Thank you.